All right, so the next topic, we haven't done Rice's theorem, and it's a little complicated. I think what we'll do is we'll state Rice's theorem and then kind of move on. All right, so if you want to see the proof of Rice's theorem, it's here. But basically, you know, we've been proving that things don't have algorithms, right? Saying, so here's a problem. It's a generic sort of problem. The input is a Turing machine, and what are we going to say about the Turing machine? We're going to say something about what the Turing machine computes, right? For example, if you asked, does it go to the fourth state, right? That sort of says what actions it takes. So you say, does it have a fourth state? Well, that's easy to check. But if you're talking about anything what the computation does, so here, then that's uncomputable. And in particular, it's saying here, suppose the input of your language is the description of a Turing machine. And what it does is it looks at the language of that Turing machine. It looks at what inputs does it accept and what inputs does it not accept. And we are going to say yes to this Turing machine if the language has some property and no if it doesn't have that property. Like, for example, this Turing machine, the language it accepts is regular, right? So that problem is just hard. And so the Rice's theorem proves that all such things are undecidable. But we're going to skip all that proof. And now we're going to talk about some other problems that are undecidable. So here's a problem. You're given, the input is a bunch of tiles, sort of like dominoes. It's exactly, we're playing dominoes here. All right? So the difference in the dominoes is that there's a string on the top of each tile and a string on the bottom of each tile. All right? And what a solution is that you lay out the dominoes in the tiles in some order. And you can repeat them. And it's really important that you can use the same tile over and over again, because if I give you a finite number of tiles, then you can try all solutions by just trying all combinations of those tiles, right? But because we allow you to repeat them, then the solution could be arbitrarily long, right? Like on the test the other day, the polynomial, does it have, can you find a solution? Can you find integer values which make it 0? Well, you can try all the solutions, but if there's an infinite number of possible solutions, then you can't try them all, right? So here, a solution will be laying out tiles, and since you can repeat tiles, the solution could be arbitrarily long, right? And what are we looking for? When is it a valid solution? A valid solution is when, after you lay out all the tiles, you look at the concatenation of the string on the top and the concatenation of the string on the bottom, and they're the exact same string, right? So here's an example. You can see that the green pieces are one tile, but if the string on the top and the string on the bottom are the same. So here, this tile here, B on the top, CA on the bottom, right? There's this tile, B on the top, CA on the bottom. And you'll see I laid them out, and then the string here is the same as this. Everybody follow that? So this problem is undecidable. And in the longer version, I have, here's one page to say how we prove it, right? Basically, if we had an algorithm for this, we wanted to come up with an algorithm for the halting problem, right? And so suppose somebody gives me a Turing machine and an input, and I want to know whether it halts or not. What I can do is I can make these little tiles that look like little pieces of the Turing machine. And what the string on the top will be, what the string is an accepting computation, right? What's the computation says? It says between this hashtag and this hashtag, it says this is what's on the tape, and the little QI here in brown or whatever color that is, that tells you which state you're in, and it tells you where the head is, right? So the head is on this character, and you're in this state. And so that's where what the computation of the Turing machine is here, and then the next time step and the next time step, right? And if the Turing machine halts on this input, then there's an accepting computation, and you can lay out the tiles to be an accepting computation. And if the Turing machine doesn't halt, then you can't lay the tiles out into an accepting computation. Right? Does that make sense? So here, we're trying to do a reduction. We're trying to prove that the domino problem is undecidable. And how do we do it? We prove that it's harder than the halting problem. Right? And what does the reduction look like? You assume you have an algorithm to solve the domino problem, and we come up with an algorithm to solve the halting problem. And to solve the halting problem, we're given a Turing machine and an input. We want to know, does it halt? And so what we do is we make all these dominoes such that if M does halt on I, then there's this way of laying out the dominoes so that it looks like a halting computation. Right? And otherwise, there's not. Right? Everybody sort of get the big picture there? So here's another version of it. In fact, it's sort of the same. We're going to do the same, but it's two-dimensional puzzle. All right? So the input are a bunch of puzzle shapes. And a solution is, again, you have to be able to, can you make a square out of these puzzle shapes? And if the square was of a fixed size, or you had a fixed number of tiles that you can only use once, then we could just brute force try all solutions, and there would be an algorithm, right? But here, we're letting you use the same tile over and over and over again, right? So here, there's only one straight tile, but I'm allowing you to use it twice, right? There's only one bend, but here we use it twice. So that allows you to make the solution as big as you want. So it can be any square, but it has to form a square, right? And so then you ask, given these tiles, can you form a square in this way? And that too is undecidable. And again, it's a reduction to the halting problem. So if the Turing machine halts, then you can write down, see the first line tells you what the Turing machine looks like at time 1. Tells you you're in the start state, the head's at the top, and the input is on the tape, right? And then time 2, time 3, until you get an accepting line at the bottom, right? So that's what, in the last example, we laid out the time steps like this, and now we're laying out the time steps like this, right? And then you fill it out with blanks so that it makes a square, right? And so if there's an accepting computation, then there's a solution that that's a square. And if there's not an accepting computation, you can't make a square, right? Does that make sense? So how do you do the reduction? Well, I assume I have an oracle that solves the tiling problems. Given tiles, can I make a square? And we design an algorithm that solves the halting problem, right? So you're given as input a Turing machine and an input. You want to know, does it halt? So you make all these tiles, and the tiles somehow tell you what the Turing machine is allowed to do, right? And also hardwired in the top of is that the input has to be the right input at the beginning, right? So that's all put into the tiles. And then if there's a solution, then the Turing machine halts. Right, people following this? In the long version of the slides, you can see I go through a whole bunch of examples here. So here the example is given a context-free grammar that you all know about. And an input, can you generate that input from that grammar? And We did the whole get term, get expression sort of algorithm. And that's a linear time algorithm, but it requires that the grammar has a feature called look-ahead 1. And we didn't really go into that, but that would be a linear time algorithm. What I normally cover in this class is a dynamic programming algorithm for it, which if you take 30-101, you'll see. And that will solve the problem for any grammar in n² cube time. All right, so that's one problem. Then you can ask a different problem. Given a grammar, does it generate every string? Right? That turns out to be undecidable. Given a grammar, does it generate some string? You see, that seems like it's a similar question. Can it generate every string? Undecidable. Can it generate some string? That's not only is it decidable, but you can do it in linear time. And then here's another one. Given two grammars, do they do the same thing? You think that's going to be undecidable or decidable? It's going to be undecidable. Why? Because all you do is you have the one grammar generate everything, right? And then wanting to know, if you knew that this grammar was the same as that, you would know whether it generated everything, right? So that's undecidable. So we're not going to go into those proofs. Oh, maybe we're going to go one line of the proof, of the undecidable proof, right? So a homework. Oh, this is something you should know. In fact, it was on the last test, right? Given two strings, are they the same? They have to be the same string. Can you generate that? And we know that you can't generate that. So that's the answer to what was on the test, right? And then on the homework assignment, which probably only one person looked at, you could here's a different problem. Given two strings like this, you generate if they're different, right? And that, it turns out, it's not too hard. You can generate that, right? So here let's talk about here's a computation of a Turing machine, right? We're given a Turing machine, and we want to know, does it halt or not? So we're asking, does it have a halting computation, right? And so here's a halting computation, right? Between the purple pound signs are the time steps, right? And what does the time step do? It says what's on the tape at that time step, and you want to know where the head is. So the head is wherever this this QI character is serving two functions. It tells you what state the Turing machine is, and by its location, it's telling you where the head is. All right, so that's a computation. And so then we can ask the question: is there a grammar which generates the accepting computations? Right? And so here's a problem. Is there an accepting computation of M on I? Right? And it turns out that do you think there's a grammar for that or not? Well, there's no grammar for it, because to be an accepting computation, this part of the tape has to be the same. To be an accepting computation, they need to be the same, right? You can't suddenly change the tape contents, right? It has to be the same with a small change, the same with a small change. But this kind of proves that there's no grammar which can do that. However, let's flip it. Let's ask, can you generate every computation, every string that's not an accepting computation, right? And then it's a little more complex, and I do it in the slides, but you can generate all of these things, all right? And so, what's our problem? Here the problem is, given a grammar, does it generate every string, right? Well, what this grammar is designed to do, let's see, here we have an oracle that solves the grammar problem, and we want an oracle that solves the halting problem, right? So you give me a machine and an input, and I come up with this grammar, and what this grammar will do is it will generate every string that's not a halting computation. Right? That's what we said we're able to do. Right? Here's a grammar that generates every string except for halting computations. Well, what happens then? If, right, here we're kind of, right, so we want to know, it says no string can be, right, if it says no, it can't generate every string, then what string can it generate? It can't generate the halting computation, right? Which tells me that the Turing machine halts. If it says it can generate every string, then I know that there's no halting computation, because it can generate every string that's not the halting computation. If it can generate every string, then the Turing machine doesn't halt. People follow that? So that's that guy. All right, here's another problem. We're going to have, let's skip ahead one here. Here we go. Everybody seen The Game of Life? It was a big hit when I was a little kid. All right, when they first developed computers to do cool things, one of the things they got them to do is to play The Game of Life. And what is it? You have, this infinite grid of cells, and some of these little cells are alive and some aren't alive. And you have some really simple rules to say, well, for every guy, I'm a guy sitting there, I'm a little cell. If the number of live neighbors I have, I look at my neighbors, and if the number of live neighbors is not 2 or 3, then I die, right? But there's a rule for, based on my neighbors, whether I come alive, a rule based when I die, some simple rules. And so then, based on the rules, it moves along, right? And so here's some examples of it doing cool things. And then you can ask a question. Given this initial configuration, you could ask, does it all die out? Or does it live forever? Or does it go off this, does it travel infinitely far? You can ask these questions, and all those questions are undecidable. All right? So basically, if you gave me a Turing machine and an input, and I want to know, does that Turing machine halt? Then I can construct a configuration of The Game of Life that kind of acts like the Turing machine, right? Because one thing about Turing machines is do I move the head or not? That's all very local decisions. So it's all encoded in this Game of Life, and I've never seen the proof. It's probably pretty hard. All right? Here's the one that I thought I don't remember ever covering it. Maybe I wrote it on the board quickly. But this was on the test, as you know. Given, if you want to know, are there real value solutions, then that's really easy. You just use calculus. In fact, you can set all but one of the variables, and you can do calculus to find a 0, right? But if you need integer solutions, right, does it have integer solutions, then that's undecidable. And if you haven't looked at the solution, the reason it's undecidable is because you can, the only obvious algorithm is you just try various integers. You just try them. And if you find a set of integers that works, then you stop and you say, fantastic. But if you don't find a bunch of integers that work, then what do? You just keep trying more integers, and at no point can you say there are no integers that work, because maybe they're bigger and bigger integers that just happen to work, right? And so I have read the proof of this, and it's at the level that I can understand it pretty well. It would kill you. All right? Found a solution, great. Otherwise, how do you know they're not larger solutions? And one thing that's interesting about this is way back before, Hilbert, before Turing was Hilbert's student, Hilbert asked, are there uncomputable problems, right? And to motivate the question, this is the problem he said. Is there an algorithm for this? Because he had a sense that, Well, if I find a solution, that's great. But if I don't find a solution, then what? Right? So this was the question he asked. And I forget the date, but I was young when they solved this. I forget. It was much later than Turing and everybody. All right? So it's not that hard of a proof.